Yeah. So, yeah, I'm Siddharth Mishra, and today's webinar is based on paradox. So, what is a paradox? A paradox is any basic confusion type. It can be an illusion, or it can be a misconception, or it can be completely unsolvable. So there are different types of paradoxes. All right. So paradox is anything that can confuse the mind. So I have thought of some, not really thought of. I have brought for you a lot of paradoxes that challenge your mind, and we'll look at the paradoxes and we'll try to solve a few of them. Because if a paradox can be solved, it's not really a paradox. It's a specific kind of paradox that is called as a veridical paradox. All right, so a veridical paradox is one that can be solved, and it's not really a paradox. There are falsidical paradox because they are not actually paradox, but they appear to be as paradoxes because of a misconception or a misunderstanding. So we'll look at many paradoxes, and it will be an interactive session. So until more participants join, let's start with a small game. So I have a game that I have come up with, and it's a really interesting game. I want a little bit of a participation. Would anybody like to participate? It's just a small game. All right, Harsh, if you can unmute yourself, I'll just allow to unmute. Just a second. Harsh, can you unmute yourself?
Hello, am I audible?
Yeah, you're audible.
Great.
All right, so I'll first explain the game and then we'll start. All right, so to explain the game, I'll take the help of my screen. All right, so it's just a small game. So we'll both say numbers, and the one which reaches 100 first wins. All right, there will be a catch which you'll know at the end. So just a small game. So the first person to reach 100 wins. So I'll write Harsh here, and I'll write Stharth, and I'll write some, I guess, here. So like I'll give you an example. Say I choose the number 1 for my first number. Harsh, choose any number between 1 and 10 that includes 1 and 10. Hello? Harsh, you're not audible. I'll just.
Yeah, you gotta give me the permission to unmute myself.
Yeah. I thought that was him. Okay, all right.
Okay,
So,
so 7.
all right. So Harsh chooses 7. That brings our total to 8. All right. So I choose the number, say 4. I choose the number 4. And Harsh, which number do you choose?
8.
Okay. So that brings our total to 8 and 12. I'm not very good at maths. 12 and 8, that brings us to 20, I think. So if you choose the number 8, I say I'll choose another number 3. Your
2.
number 2. So 23 plus 2, it's 25. Say I'll choose the number 9.
3.
25 plus 9 is 34, and 34 plus 3 is 37. 30, oh, sorry, 37. So you chose the number 3. So I'll choose now, I'll say 8. 8 is a good number. I choose 8.
Okay, I'll choose 10.
All right, you choose 10. So 37 plus 8 makes 45, and 10, 55. So then I choose 1.
I choose 3.
51, 56, 56 and 3, 59. Sorry, 59. I'll choose 8. So if I choose 8, that makes it 67. What number do you
9.
choose? Making it hard to add. 67 and 9 is, I think, 76. So this time I'll choose 2. That makes it 78. What number do you choose?
5.
78 and 5 is 83. So I'll choose the number 6. That brings us
Uh,
to a total of 89.
okay, so basically, I think I'm in a scenario where if I choose any number, you will be able to counter with a number that will make the sum 10. So, like if I choose 7.
Okay. If you choose 7, then I'll choose, okay, the 7, the sum gets 96, and I'll choose 4. So I win. That makes
Yep.
100 first. So I think that was a coincidence. So nah, I guess it was a coincidence. We'll try again. All right. Anybody else want to volunteer? So I see Sarthak here. Sarthak, would you like to volunteer for the game? Yeah. Hello, Sarthak. Did you understand the game?
Hi. Yes.
Okay, so we'll start again. I'll just let me erase the numbers again. So I'll just repeat the instructions one more time, and then we'll start. All right.
Okay.
So uh, we'll start with a number, and then we'll both choose numbers between 1 and 10, both included. You can choose 1 and 10 both also, and then the first one to reach 100 wins. So say I choose 1 again. All right. So what's your number? Oh, sorry. I'll just allow to unmute.
Yeah. Sorry about that.
Yeah, no problems. I chose 1.
So 2.
Okay, you choose 2. So that makes the sum 3. Then I choose 9.
Okay. So 5.
You choose 5. Okay, so the sum gets 17. And I choose 6. That makes it 23.
3.
All right, 3. 23 and 3 is 26. I'll choose 8. That gets it to 34.
So 1.
Okay, 1. You choose 1. That makes it 35. I'll go high. I'll take 10.
8.
45 and 8 is 53. I'll choose 3. That makes it 56.
So 7. Yeah.
You choose 7.
Yeah.
56 and 7 is 63. Just a second. 67. I'll choose 4. Yep.
I think you did the calculation part wrong.
That is highly
Somebody is
likely.
saying that. I'm not
That is highly
sure.
likely. 3 and 12, 17. 17 and 6 is 23. 23. I can't figure it out. We'll start again. No problems. If there was a calculation mistake, we'll start again. Okay. So yeah, I choose 1. Sarthak, your number?
7.
7. That makes us 8. So I'll choose 4.
9.
9. 7 and 1 is 8. 8 and 4, 12. And 9, 21. So I'll choose 2.
5.
5. All right. So 21 and 2, 23. And 5, 28. I'll be careful this time. 5 and say 6.
2.
28 and 6, 34. And 2, 36. I think I'm going correct this time. 34. Yeah, 36. So you choose 2. I'll say 9. 36 and 9 makes 45. Your number?
4.
49 it is. So I'll choose 7, I think.
10.
56. 56 and 10 is 66. So I'll choose 1.
9.
66, 67. 67 and 9 is, I think it's 76. So I'll choose 2. That makes it 78.
5.
And 5. That makes it 83. So I'll choose 6 this time. That brings us
Okay.
to 89.
So 2.
Okay, you choose 2. That makes it 91, and I choose 9, and I think I win. That makes it 100. That made it 91.
Okay. Is this a
So,
coincidence? Like
nah,
2 times
that's
2.
not a coincidence. I was playing with you. So the if somebody looked at if somebody looked carefully at the numbers, you'll see a pattern. I started with 1, and then there was 7 and 4. That makes 11, and then 9 and 2, 5 and 6, 2 and 9, 4 and 7. Missed one. 10 and 1, 9 and 2, 5 and 6, 2 and 9. So basically, whatever number Sarthak was choosing, I was subtracting it from 11, and then I was choosing the number that was the difference. So how did that work? So I thought of a series first. All right. So I started with 1, and then I wrote 12, 23, 34. I think that's 45, 56, 67, 78, 89, 100. So this is an arithmetic progression, a simple pattern series. The numbers are separated by 11. So I just had to ensure to reach 11. On my turn, I had to be on. I had to be on this series, right? So when I chose 1, Sarthak chose whatever number Sarthak chose. I just subtracted it from 11. So the difference would be my number, and I would land at 12. So if you see the sum, all right. So 1 and Sarthak chose 7. So I chose 4. That makes it 12. So every time I landed on these numbers. If I landed on these numbers, I was going on the right pattern. So you cannot escape the pattern because the difference is 11. You'll have to either choose a number between 1 and 10, right? So I'll choose any number that counters your number, and I'll be on the pattern. There can be a slight trick if you want to play with your friends. If you play it twice or thrice times, you'll see that I'm starting with 1. So you can change it if they're starting to suspect. So you don't start with 1, you start with say 2, and then you keep on saying random numbers, and until you get a point. Say Sarthak, the sum was at a number 35. So I chose the number 10, and then I came back on track to 45. So the sum will continue, and they'll not suspect these starting numbers. So this was a little. This was just to make make the mood for the webinar. It's just a simple misconception. So it's something that you couldn't notice it. So paradoxes are basically, some paradoxes are that, others pose very big issues, like in time travel and stuff. So now we'll start with the main topic of the webinar. Just change the screen. Just a second. Yeah. All right. So the first kind of a paradox is the potato paradox. So I will make the session a little bit interactive. So the potato paradox is basically a question. So I say that I'm a farmer and I have 100 kg of potatoes. So I have the potatoes, and the potatoes are comprised of 99% water and 1% solid. All right. The mass of the potato is 99% the mass of water, and the 1% remaining is solid. So if I have to make the potatoes say 98% water, I have to remove 1% of water from them. All right. So I have to decrease the percentage of water from 99 to 98. So how much would the final mass be? Final mass of the potatoes would be. It was initially 100, and they were comprised of 99% 99% water and 1% solid. All right. If I have to decrease the water composition by 1%, so what would be the final mass? Any guesses or any answers? If you can't get the answer, it's matlab, you can always guess. It's not a quiz. Yeah. It's actually not 1%. I'll repeat the question again. All right. So we have 100 kg of potatoes, and the mass of the potatoes is 99% water, and 1% is the mass of solids. So I have to decrease the composition to 98% water and 2% solids. So what would be the final mass of my mixture? Some water would obviously be evaporated, so there would be a decrease in a bit of mass. Any guesses to the final answer? I'm asking the final mass, not the final percentage. See, it's initially 100 kgs. All right. So some water would be evaporated. So if some water would be evaporated from the potatoes, it will obviously lose mass. All right. The content of the potato would not increase. 99 kgs is the obvious answer, but not the correct one. That's what a paradox is about. It's not really a paradox, just a tricky question. I'll tell the answer. Okay. So the final mass of the potatoes would be 50 kgs. It was initially 100 kgs. We removed 1% water, and it became 50 kgs. So how would that be? So that was a little bit of trick. See, I'll explain. We had 100 kg of potatoes, right? So I say that it's 99% water, which implies it's 99 kg water, and it's 1% solid. That implies 1 kg of solid. So let's take the final mass of the potatoes to be say X. All right. So the water would be evaporated. So I don't know how much water would be evaporated. That's a bit of a question. But the trick here is that the solid would remain same. So the solid was initially 1% and 1 kg, and finally it would be 2%. So final composition is 98 and 2, right? So that 1 kg solid would make up to be 2%. So I'll just write a simple equation. that is 2% of x is 1 kg. So that makes it 2 by 100 into x is 1, 2x is 100, x is 50 kgs. So the final mass of the potatoes comes out to be 50 kgs. That was not a bit of a paradox, but still it was a good question. So the common sense says that it should be 99 kgs because 1% water evaporated. But the trick was in the question that the final composition of solid is also 2%. So the final mass of the mixture becomes 50 kgs. It's called the potato paradox. So as the farmer is really confused as to where the mass of the mixture went. So the next paradox we'll be looking at, I just have to give a brief background. The initial paradox we're starting are called as falsidical paradoxes. These paradoxes are not really paradoxes, but seem false due to misconception or misunderstanding of the concept, right? So we looked at this potato paradox, right? So it was not a paradox, it was just a misconception. Another paradox is called as the it's called as the Achilles and the tortoise paradox. I'll rename it to the Usain Bolt and the tortoise paradox. All right. So we have a worldwide, an international race between the world's fastest runner Usain Bolt and the slowest animal tortoise. So to give the tortoise a bit of a head start, they start at a distance of say 50 meters in a 100-meter race. Here's the tortoise. I don't know how to draw one, so I'll denote it by T. And here's Bolt. I'll denote him by B. So tortoise at the head start of 50 meters. Bolt runs all the way after just say 4-5 seconds, and he reaches the tortoise. But the tortoise is a bit ahead of him. So here is Bolt, here is tortoise. There is a gap of the last 1 meter between them. So all right. So if I try to divide the distance Bolt is yet to cover, the Bolt will cover this half of a distance in some finite time, and then the remaining would have also a half. That would be 1/4, and then very sorry, is the screen visible, right? Yeah. So if you try to divide the distance the Bolt has yet to cover, I'll just enlarge it on a line. So here is Bolt and here is tortoise. So he'll cover the first half meter remaining to beat the tortoise. Then he'll be left with this distance. This will also have a half. So if this is 1/2, say he takes 1 second to cover, to simplify calculations. Here he'll take 1/2 seconds. Then here he'll take 1/4 seconds, and then so on, so on. There will be in an infinite term that will be decreasing by 2, or at 1/2 plus 1/4, and then 4 half is 8, 1/16. So he'll take a finite amount of time in all those intervals. So how can he actually pass a tortoise? He has a finite amount of time in infinite intervals. So finite, 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 we added infinite times. So how could he pass the tortoise? But if you look at the real life scenario, it takes him mere amount of milliseconds to pass the tortoise. All right. So how can he pass the seconds if an infinite amount of time is required? So the concept behind this is that an infinite amount of small numbers can be added to make a finite number. So I think a better explanation would be from a video. I'll share my screen just for a. It's a great video and it'll help you. The video is about another paradox. All right. It's on similar basis. It's just a second. Yeah, it's on a similar basis and it's called as Zenos Paradox. All right. So Zenos Paradox states that it's on a similar basis, all just the same. So Zeno was a man and he was in his front door. He saw a tree outside. Forgive me for my drawing. I'll just write tree. So he saw a tree outside and it was at a distance of say 1 meter. All right, so we'll take Zeno to be a very slow person for us to simplify calculations. So then he takes an hour to reach that tree. All right, so he says that to cover the first half, I'll take 1/2 hour. Then another half will remain, and that would also have a half. So this is 1/4. This is 1/16. So I'll just keep covering finite distances in finite time for an infinite amount of period. So how can I actually reach the tree? So this is explained in a great manner in a video. I'll just share my screen and please confirm if it would be visible. Share screen. Just a second. I think the video is visible. So audible as well. I'll share it again. Kindly let me know if the video is audible as well.
This is Zeno of Elia.
Is the video audible? If it would be really helpful if someone could confirm on the chat. All right, thanks.
Ancient Greek philosopher famous for inventing a number of paradoxes, arguments that seem logical but whose conclusion is absurd or contradictory. For more than 2,000 years, Zeno's mind-bending riddles have inspired mathematicians and philosophers to better understand the nature of infinity. One of the best known of Zeno's problems is called the dichotomy paradox, which means the paradox of cutting in two in ancient Greek. It goes something like this. After a long day of sitting around thinking, Zeno decides to walk from his house to the park. The fresh air clears his mind and helps him think better. In order to get to the park, he first has to get halfway to the park. This portion of his journey takes some finite amount of time. Once he gets to the halfway point, he needs to walk half the remaining distance. Again, this takes a finite amount of time. Once he gets there, he still needs to walk half the distance that's left, which takes another finite amount of time. This happens again and again and again. You can see that we can keep going like this forever, dividing whatever distance is left into smaller and smaller pieces, each of which takes some finite time to traverse. So, how long does it take Zeno to get to the park? Well, to find out, we need to add the times of each of the pieces of the journey. The problem is, there are infinitely many of these finite-sized pieces. So, shouldn't the total time be infinity? This argument, by the way, is completely general. It says that travelling from any location to any other location should take an infinite amount of time. In other words, it says that all motion is impossible. This conclusion is clearly absurd, but where's the flaw in the logic? To resolve the paradox, it helps to turn the story into a math problem. Let's suppose that Zeno's house is 1 mile from the park, and that Zeno walks at 1 mile per hour. Common sense tells us that the time for the journey should be 1 hour. But let's look at things from Zeno's point of view and divide up the journey into pieces. The first half of the journey takes half an hour. The next part takes quarter of an hour. The third part takes an eighth of an hour, and so on. Summing up all these times, we get a series that looks like this. Now, Zeno might say, since there are infinitely many terms on the right-hand side of the equation, and each individual term is finite, the sum should equal infinity, right? This is the problem with Zeno's argument. As mathematicians have since realized, it is possible to add up infinitely many finite-sized terms and still get a finite answer. How, you ask? Well, let's think of it this way. Let's start with a square that has area 1 unit. Now let's chop the square in half, and then chop the remaining half in half, and so on. While we're doing this, let's keep track of the areas of the pieces. The first slice makes 2 parts, each with an area of 1/2. The next slice divides one of those halves in half, and so on. But no matter how many times we slice up the boxes, the total area is still the sum of the areas of all the pieces. Now you can see why we chose this particular way of cutting up the square. We've obtained the same infinite series as we had for the time of Zeno's journey. As we construct more and more blue pieces, to use the math jargon, as we take the limit as n tends to infinity, the entire square becomes covered with blue. But the area of the square is just 1 unit, and so the infinite sum must equal 1. Going back to Zeno's journey, we can now see how the paradox is resolved. Not only does the infinite series sum to a finite answer, but that finite answer is the same one that common sense tells us is true. Zeno's journey takes 1 hour.
Yeah, so this was the Zenos paradox. So we saw that an infinite amount of numbers make the sum a finite, they tend to a finite value. It was a beautiful example through a square. So this kind of a paradox is called as a falsidical paradox. It's not really a paradox, but the concept behind it is really unknown to us, and there's a misconception. So Zeno thought that there are finite amount of time. So if we add finite amount of time, infinite times, so answer would be infinity. That was general logic. So that would make a real motion impossible. So they had to come up with the solution. So this was a falsidical paradox. If we go beyond that, there are many other paradoxes. For example, there are some interesting results that can be called a paradox. They're just mind-blowing. All right, so I give you an example. Say there is a group of 23 completely random people. You take 23 people out of Earth and then you put them in a spaceship. So you ask the 23 people what's their birthdays. So you collect all their birth dates and you put them on a piece of paper. So what's the mathematical probability that two of them would be born on the same day? All right. So it's just a basic common sense question. So what would be the probability that two of them share the same birthday? So common sense would tell us that there are 23 people. There are 365 days in a year. So the probability should be around 23 upon 65, 23 upon 365. That comes out to be around, just a second. Yeah, that comes out to be around 6%. So if you go with common sense, that says 6%. But actually, that's not true. If you mathematically calculate the probability, it comes out to be 50%. There's a half a chance that two of them would share the same birthday. There are just 23 people and there are 365 days, but there is a 50% chance that they'll share the same birthday. If anybody would like to inquire about the mathematics, they can stay back after the webinar. It's just basic probability. It just takes multiplication, but the calculation is a bit complex. So after the webinar, if you really want to learn the mathematics, I'll tell you. Just drop a message in the chat after the webinar ends. All right. So this is a birthday paradox, right? So there are 23 people and the chance of their common birthday is 50%. If you hire the number, say there are 75 people. All right. So there are 75 people in a group and there are 365 days. So the common sense of the probability of two of them sharing the same birthday would be 75 divided by 365. That would come out to be around 0.2, 20%. So there's a 20% chance of two people sharing a birthday. But if you mathematically calculate the probability, it comes out to be 99.97%. So 99.97% chance there is for two people to have the same birthday. It's basic mathematics. If anybody would like to inquire about the mathematics, I'll be gladly doing that. So another question, this is for you all guys. This is not a paradox, just a basic question. So if I ask you, there are two types of numbers, all right? One is the type of number that is called as a perfect square, and the other is not a perfect square, non-perfect square numbers, all right? So if I ask you, are the number of non-perfect square numbers greater than the number of perfect squares, or are they equal, or what's the case? So the number of non-perfect numbers like 2, 3, 5, 6, 7, 8 and onward 10, these are not a perfect squares. All right. So the number of which of these sets is more? So we have a set of whole numbers and we assign the tags. All right. There's a perfect square. There's not a perfect square. All right. So the numbers like 2, 3, 5, which are not perfect squares, are they more in number or what? It's just a question for the chat. Let me access the chat window. Atikir says it's non-perfect greater than perfect. Okay, we'll come back. All right. Palak says it's equal. Yes, Nandika, you can answer. Yeah, Yonat, you're perfectly correct. That was the trick. I'll share the screen. Yeah, that would be equal. Yes. I'll explain it. Just let me share my screen. Share. There's some issue. Just a second. Until there's some issue with my laptop, so I'll just verbally explain it. So basically, you look at this. Yonat perfectly explained it. So they should be equal. For every number, there would be a perfect square. So if you assign a tag to a non-perfect square, at the same time, you will have to assign the corresponding square another tag of a perfect square. So if you keep on assigning tags, they'll go on to infinity and they'll be equal, right? So non-perfect score will not be greater, as a few of you wrote on the chat. There are infinite numbers. Yeah. Nandika, you're perfectly correct. There are infinite numbers and each number has a square. Yeah, that's the correct reason. So after that, we move on to the last of the falsitical paradoxes. The falsitical paradoxes are basically questions, not paradoxes. So this is the basic mental ability question. So imagine that a family has two children, one of whom, who is the elder son, is known to be a boy. What is then the probability that the other child is also a boy? All right. So there is a family, and then we have to say that the first of their son is a first of their child is a son. What's the probability that the other child is also a boy? So I'll look in the chat for answers. Yeah, basic answers are coming 50%, 50%. Any other guesses or answers if you have calculated? I'll tab tak work on my screen. Okay, so the most of the options are coming as 50%. Any other guesses? All right. So yeah, I got all the answers as 50%. So actually the answer would be 66%. There'll be a third chance of a boy. Sorry, 33%. There would be 1/3 chance that the other son would be a boy. How is that? So if you look at them initially, so the couple say C they had two children. All right. So what would be the initial possible situations? So there could be say boy boy. That could be boy girl. That could be girl boy. That could be girl girl. All right. So if we know that this is a boy, all right, so if we know that this is a boy, we can eliminate like this probability and this probability. No, we can eliminate this boy girl. So the remaining probabilities would be boy girl, girl boy. No, this would not be there. Boy boy. So if you look at the cases, you'll see that there's this third chance of that being a boy. All right. So if the second son has to be girl, girl, and boy, so there are three cases, and only in one of them is the third son boy. If you're able to understand it, like see, we have three possible situations. They can't be girl boy because we know the first son is boy. All right. First child is boy. I'm really sorry. So there are three possible cases, and only in one of them is the third child boy. So there's only a third chance, not 50%. So it's 33% chance. You could always use that in bets also. If you say that you have to choose two numbers out of four, if you choose one number and then you have to choose the second number, so you'll think that the second number would be, they'll all have a 50% chance. But if you look at them closely, the chances of one of them would be higher because we know it's a boy. The first one being a boy, that helps us actually. All right, so the chance would come out to be 1/3, 33%. So this is a bit of a tricky situation. It's not a paradox because we can explain it. Now we can move on to some paradoxes that we can't explain. All right, so they're true paradoxes. For example, we start with the most basic one that I tried to explain in the message also yesterday. We'll name it the Sarthak's paradox. All right, so is Sarthak trying to tell the is Sarthak lying or is he telling the truth? So if I write Sarthak issues a statement saying I am lying. All right, Sarthak says I am lying. So is he actually telling the truth or is he lying? We'll analyze all the situations. So if Sarthak is being truthful, all right, he's being a good citizen and he is being truthful. So we'll say that just a second. Yeah, if Sarthak is telling the truth, all right, if Sarthak is telling the truth, that means the statement would be true. That means he is lying because the statement says that he is lying. So, but if the statement is true, then he is lying. If he is lying, then how can he be telling the truth? All right, so that was the wrong option. So if he can't be telling the truth, then he must be lying. If he is lying, then his statement I am lying would be false. So indeed he is actually telling the truth. If he's telling the truth, that means his statement would be true. That means he would be lying as he said in the statement. And if he is lying, then his statement would be false. If his statement is false, then it means that he is telling the truth, because in his statement he says that I am lying. So an endless loop of this paradox is created, and we cannot determine what Sarthak is trying to convince. So either Sarthak is really clever or really dumb to issue such a statement. All right, so we'll move on to the next unsolvable paradox, the grandfather's paradox. Grandfather's paradox I explained in the previous webinar also. It's a paradox associated with time travel to the past. So it's the situation basically is I'll try to explain that I'll try to explain it in a better manner that does not make you kill your grandfather. All right, so you make a time machine and you decide to go back to when your grandfather was playing in his childhood. You have heard really good stories about his childhood, being in a park. So you decide to go on that actual date when he was in the park, and you take the time machine, and when you land the time machine on that particular time, you actually by mistake land on your grandfather. All right, so the spaceship comes out of this hole, and here your grandfather was playing, and you actually landed on him and crushed him to death. All right, so your grandfather is dead now. So what happens next? Your grandfather was in his childhood, so that must mean that he'll not marry your grandmother. So here is his grandfather, grandmother. I'll just basically make a chart and explain it to you. So there have your dad, mom, and that makes you. All right, so you crushed your grandfather. That means your grandfather is dead. All right, so that means he does not meet your grandmother. Okay, so he does not meet your grandmother, and then that means your dad is never born. If your dad is never born, that means you are never born. So if you are never born, that you cannot kill your grandfather, right? If you're never born, how can you kill your own grandfather? So that means your grandfather should be alive. So we'll write grandfather back here. All right, so that means your grandfather is actually alive. He marries your grandmother, your dad is born, and then finally you will be born. If you are born, then you go kill your grandfather in this situation. So all right, so that means grandfather must be really dead. So if grandfather is dead, that means your dad is dead. That means you are never born. All right, if you are never born, then we can go on and on and on, and there's no possible outcome to this. All right, so there's a solution by Minute Physics on YouTube that's a bit complicated for this webinar. It deals with the possibility of both of these situations being true. All right, so there's also a situation that you go into a parallel universe and kill your own grandfather, but that situation then does not seem fun, because that would not be your past technically. It would be an alternate universe where you'd be traveling. All right, so you actually don't kill your own grandfather, but that's not really for this webinar. So this paradox is actually unsolvable until now. So the next paradox is the bootstrap paradox. The bootstrap paradox is really popularly used in all the movies and sci-fi movies. So the bootstrap paradox, I'll explain it with two examples. First example I used in the last webinar was of a book. So you wake up one morning and you have a package that's saying for you. The package has your name, right? You open the package and there's a book that states, just a second. Sorry for the disturbance. So that's the bootstrap paradox. All right, so you have a book and it's titled how to make a time machine. You make a time machine, you spend 10 years, and you take the time machine and you decide to go back to the past when the book was received, so that you can actually make the time machine again. So you decide to go back to the past, you take the book and you keep it on your front door as a package for you. So you get that book, you again make a time machine. So endless loop of time is formed, right? So you receive the book, you make the time machine, and you put back the book. So in this scenario, the book really never exists. All right, you keep the book at the front door because you're in the future, and endless loop is formed. All right, so you take the book, you make the time machine, and you keep back the book. So where was the book from in the first place? If this is a little bit tricky, I'll try to explain it with another example. Say you're a science student, you learn about Newton's theory of gravity. All right, so you are intrigued by the Newton's theory of gravity, and somehow your dad has a time machine and you take the time machine and go back to the past. You meet Newton and you tell him your theory. All right, so this is before he actually came up with the theory of gravitation. So you tell him the theory of gravitation. So he publishes that theory and he is world famous, and then you learn about the theory. So how did this information come to the universe in the first place? All right, so you told Newton the theory and you actually learned it from Newton himself. All right, so where was this information actually in the universe? It really never exists. So this is the Bootstrap Paradox. The last paradox we'll dealing be today is the Classless Paradox. It's a great paradox for students. It's about a surprise test by the teacher. All right, so imagine the situation. The class teacher says that students will have a test next week. It will be of complete surprise, and it can be on any day of the week. All right, so she says this on Friday, and she says that you'll have a surprise test on any day of the week, and you'll have no further notice about it. All right, that's a surprise test. So you all of you are tensed, and suddenly one boy shouts that there will be no test. So how can that be? I'll try to explain it with this situation. All right, so there is Monday, Tuesday. Just a second, I'll try to improve my handwriting. Monday, Tuesday, Wednesday, Thursday, and Friday. All right, so these are the possible dates for a test. So the test cannot be on Friday. Right? If the test is on Friday, then you'll know it by Thursday evening, because the test would not have been done in the first 4 days. So you'll know it on the day before Friday, and hence it will not be a surprise test. All right, so that means Friday is out of the picture. If the test is not on Friday, you know Friday is out of the picture. Then if you don't receive the test by Wednesday, you'll know it is on Thursday. So if the test is on Thursday, that would not be a surprise for you. So that way Thursday is also out of the picture. Thursday out of the picture, and Wednesday is also out, Tuesday and Monday. So that means there would be no test. But to the children's surprise, the teacher comes on Wednesday morning and hands them the test. So how is that possible? We logically eliminated all the days, but still they get the test. So it's a unsolvable type of paradox, and there is no complete solution as of now that I know of. So this was the Classless Paradox. So that's it for today. I discussed a lot of paradoxes, and we played a short game based on mathematics. So it was more of a mathematical session. I thank you all for joining. And if you have any questions, any doubts, you can just unmute yourself or take the chat. The chat is allowed. So you can chat. You can use the chat window to ask any questions. The webinar is over. I'll just stop my screen sharing. I explained the math behind solvable paradoxes. Which one of them are you asking about? Which of the paradox? Are you asking about that? Which was that? The birthday paradox. Boy-girl problem. All right. I'll. Why did I stop screen sharing? Sorry. I'll explain about the birthday problem at the last. That's a bit of complex mathematics. It requires this basic permutation and combination. I'll try to explain it at the end. But before that, if you have any questions from this webinar or the last one, you're free to discuss. The chat window stays open. I'll just check once if there are any questions. Yeah, there's just mathematical questions. If you want me to repeat any part or anything, you can just write in the chat box. All right, so I don't think I'm getting any other questions. So yeah, I'll try to explain the maths. Sarthak, right? Yeah. Yeah, Jasleen, what's the question? I can provide you the option to unmute also. I'll just do that. You'll have to type the question. Jasleen, you wanted to ask a question?
Yeah.
Yeah.
Sir, we didn't receive any task or something
Task regarding what actually?
regarding the organization.
No, this is a webinar series. You don't have to fill the webinar journal or anything. So it's just a webinar series. You don't receive tasks.
Okay, sir.
Yeah.
Thank you.
Yeah. No